Hello everyone, myself Aditi and today I am back with another LeetCode's daily challenge problem. Here the question is, in this question basically you are given a set of n binary tree nodes which are numbered from 0 to n minus 1 and every node I has two children, that is the left child and the right child. You are asked to return true if and only if all the given nodes form exactly one valid binary tree. And in the question it is given if a node doesn't have a left child, then left child will be equal to minus 1. Okay, so you have to just assume it as minus 1, and similarly you have to do it for the right child. For example, if the right child for a node I isn't available, then you will use a value of minus 1 for it. Okay, and you have to note that the nodes have no values, and that is we only have to use the node numbers in the problem. That is, we just have to use their indexes because no values are assigned to them. Fine, so let's start the implementation part. Before implementing, let me tell you the valid conditions, or you can say the important or required conditions, the necessary conditions for a tree to be a valid binary tree. The conditions are such that the one node must not contain a parent. And what do you think by this? What do I mean? I just simply mean that there has to be a node in the binary tree which does not contain a parent, that is the root node. Okay, so the root node is the parent of the all sub present nodes in the tree. So the root node will be the parent and will not contain a parent for itself. Fine. So there has to be a node which must not contain a parent, which is the root node. Secondly, there is a condition that the nodes should be connected. They should be connected. That is, they should not be disconnected. Okay. Also, there has to be condition that nodes must not form a cycle. Okay. That is, it should be an acyclic structure. I hope this is clear to you. Now let's start implementing. So first of all, what are we going to do? First of all, we'll create a hash set. Okay, in that we are going to store the nodes which have at least one child. Fine. So let's create a hash set of integers. Let's name it as has parent. Okay, so we have created a hash set of name has parent, and we are going to iterate. We are starting our for loop from here. We are going to iterate through the loop starting from node value equal to node number is equal to 0 till n minus 1 because the nodes are numbered from 0 to n minus 1, hence n nodes. Fine. So yeah, we are going to run our loop from 0 to n minus 1, and we are going to check two conditions. If a node's left child exists, that is, it is not equal to minus 1, what are we going to do? We are going to add that left child to our hash set named has parent. Fine, we are going to repeat the same thing for our right child as well. Okay, so we have first of all created a hash set named has parent, and then we have started our loops iterating from node equal to 0 up to n minus 1, and then for each node we are going to check if it contains left child and then if it contains the right child. If it contains, then we will add the values of corresponding child or corresponding children of it to the hash set. Okay, then what are we going to do? We are going to check, after the loop is over, we are going to check if the size of has parent hash set has parent dot size, if its size becomes equal to n. What do you think? What we need to return? We need to return false here. Why? The reason is, if the size of our created a hash set has parent becomes equal to n, and n is nothing but the total number of nodes available in the tree. If it becomes equal to n, what does that mean? It means that every node has children, or vice versa, you can say that every child has a parent. So what do you think? If every child has a parent, then do you think that's a valid binary tree? Obviously not, because we just mentioned that one node must be there which should not contain a parent. So this means if the size of the hash set becomes equal to n, that's not a valid binary tree. We will simply return false here. Okay, and after that, since we have not found out the root, or you can say there are multiple roots existing for one node or for its children, then that's not a valid binary tree. So we are returning false here. So we are initializing the value of our root as -1, because we have to keep track of the original node, right? So yeah, we have done this, and we have checked first of all, yeah, we have checked for right child and added to the hash set. Then we have checked for multiple roots. Then we have initialized a root variable as -1, and this will be simply used to keep track of the root node, you can say. And we will loop through all the nodes again to find the node without a parent. Okay, so what are we going to do? We will again iterate through the loop, starting from node value or the node number I equal to 0 up to n-1, and we will find a node I which is not contained in the you can say which is actually present without a parent. Okay, so we are again iterating through the loop to find the node without a parent, and then what are we going to do? We will check if has parent doesn't contain our node I. If it doesn't contain, what does that mean? If our hash set called has parent doesn't contain I, that simply means that it is not present in the hash set, that is, it doesn't have a parent. So since we found out the node which doesn't have a parent, we simply say that we have already found the root. So we can initialize, or we can assign the value of root as I. Okay, so the node value I which doesn't contain a parent is the root value itself, or you can say the root node itself. Now since we have found out the root, we will break here. Fine, because we were just iterating through the loop once again just to find the root. Fine, now what are we going to do? We are going to create another hash set of integers called visited, okay, to keep track of the visited nodes. So yeah, we have again created a hash set for visited nodes, and we are just doing it in order to keep track of visited nodes during the DFS search. Okay, now we are beginning the DFS search here. In the DFS search, we are calling DFS method for the root node, okay, for the root node, for the visited hash set, for our left child, and for the right child. Okay, and with this we will also check if the size of our visited hash set is equal to n or not, because in this hash set, what do you think? If you have to visit each node present in the tree, then it has to be equal to n, right? So if it is equal to n, and if you have called the DFS method for root, for the visited integers, for the left child, for the right child, and if this condition is true, only then we will return true. Fine. So basically now, yeah, now we are again defining a recursive method boolean DFS, which takes arguments as our current node index I. We are taking our argument visited hash set, okay, and we are here taking the array of left child as our argument. We are also taking our array of right child as our argument. Okay, now in this we will check for the base case. What should be the base case? If I is -1, what does that mean? If the current node is a leaf node, then I will be -1. What does that mean? That is, it doesn't have any children. So if it is -1, we will return true. Okay, that means the leaf node doesn't have a children, so we will return true, and this to indicate that it's a valid leaf. Fine. Now we are going to check for cycle. I already said in the beginning that the nodes should be connected, they should not be disconnected, but they should not form a cycle as well, because if they form a cycle, the condition for a valid binary tree is not met. So we are going to check if the node that we are searching for is already present. If it is already present in the visited hash set, that means that there is something like a cycle, or you can say that it is becoming a cycle. So it should not be present in the visited hash set. Okay, so in simple words, you can say if a current node has already been visited, you can say it implies a cycle in the tree. So you will return false here. Okay, and obviously if it doesn't contain, then you will just add that specific node in, or you can say node number I, to the visited hash set. Now you are just asked to return DFS for. Okay, so you will recursively travel for the left and the right subtrees. To traverse for the left subtree, we are going to take argument or input as our left child for the specific node that we are searching, our visited hash set. Okay, so we are recursively calling it for the left child, recursively calling for the left child, and also we are recursively calling for the right child. Okay, and only if the left subtree and the right subtree are valid, you can return true. Okay, if both the left and right subtree are valid, then you can form a valid one binary tree, exactly one valid binary tree. Okay, so that's the reason to return true we have used the AND operator here. Let's try to run the code. Okay, so okay, there is some error, as parent dot contains. Okay. There is one more error. There is some spelling error. Okay, so the code is accepted, and now let's try to submit it. So yeah, the code is accepted. Stay tuned, guys. Thank you for watching.